Let's call our second speaker, Stefan Manner from University of Kassel, who is going to present IPD, Detecting Traffic Ingress Points at ISPs. Stefan is near completion of his PhD and has already started an industrial career at Sonocrit. Since 2019, Stefan has been working with Oliver Hoffel on different aspects of both industrial networks and the internet from a measurement perspective, with the present paper being related to the measurement perspective, of course. So the floor is yours.
Thank you and welcome. Yep, the clicker is not working. Okay. Sorry. Hello and welcome. I'm Stefan, and today I want to present our joint work with Venox on how to detect traffic ingress points at ISPs. And why this is a relevant problem, I want to show you in a small example. As an ISP, you may be faced with seemingly weird network performance issues, such as the following. In a certain city, ISP provides internet access for both ADSL and fiber to the home customers. At some point in time, the fiber to the home customers experience a degradation in network performance for one particular website, whereas the ADSL users do not have any problems. And the reason for that is the following. The website is served by a CDN. CDNs operate networks of globally distributed network data centers to bring the content as close as possible to the users. And here is the actual problem. The ADSL customers served via a nearby data center, whereas the fiber to the home users are served by a data center thousands of kilometers away. And here the actual problem is that the CDN did a wrong mapping to the fiber to the home customers or prefixes. And ingress point detection is a solution that enables to detect such kind of problems. Another use case of ingress point detection is to implement better traffic engineering schemes, such as joint CDN ISP traffic steering. In this situation, the ISP and the CDN both collaborate to find optimal links for receiving traffics. This, of course, requires the ISP to detect where traffic actually enters the network. And this can be a complex task, since traffic can enter the network via NEAS, not necessarily directly from the CDN. And here, ingress point detection is a tool that helps to enable such a use case. So, if you want to implement ingress point detection, you're faced with a bunch of challenges. And the first one is scale. Because it is necessary to monitor traffic from all the border routers of the ISP's network, which are thousands in the case of the observed ISP. And another question is about granularity. So at what granularity you want to observe and track the traffic? The problem here is tracking the ingress points on the base of individual IPs does not scale. So what tracking granularity? So we need to aggregate the IP addresses to IPD ranges and that share the same ingress point. But what granularity should be applied here? And the answer is it depends. In case of the CDN traffic steering scenario, the collaborating CDN maps the data centers to up to /28 networks. So it's necessary to track the granularity at least at the CDN tracking mapping granularity. And for efficiency reasons, we require the algorithm to adapt the granularity to the actual traffic dynamics that which means that we aggregate the ranges that share the same ingress point. one may ask now, why not simply use BGP for that, since BGP data is easy to obtain? The first problem we already discussed in the previous slide. We need a tracking granularity that is more specific than BGP usually announces. And another problem is the following. Let's assume the ISP announces its address space on all the egress links that are shown here. Simply because the ISP is making such announcements, it does not necessarily mean that subsequent traffic also enters over all the links. And the very same is true for the announcement of the receiving of the neighboring ASs. So to better understand the traffic dynamics, we first performed the measurement study. Here we found out that the ingress points change often. So in 60% of the cases, the prefixes are quite stable for less than 1 hour. And in only 10% of the cases, the ingress points are stable for more than 6 hours. So it is necessary to run the algorithm regularly. And we also found out that in most cases, for a given prefix, there's only one ingress point for a certain time, even if BGP announces multiple passes. And if there's more than one ingress point, in many cases, only one is dominant. So we saw that in 80% of the prefixes with more than one ingress point, 80% of the traffic ingresses over that single one. So we want the algorithm further to be able to detect the dominant ingress links. So let's summarize our design requirements. The IPD algorithm is a scheme that performs a traffic-based partitioning of the IP address space. Since BGP cannot be used for that, we solely rely on NetFlow. Further, this algorithm needs to scale out to thousands of routers. And our scope is to detect all the ingress points, and for efficiency, we only track the source IP of the incoming traffic. We focus on the dominant ingress points of the high traffic prefixes, since these are the prefixes that have the most impact for traffic engineering. With that, we come to a systems design that consists of 2 stages. In the first stage, the massive influx of NetFlow is handled. Here, the goal is to collect the data and put it in our data structure. In the second stage, we analyze the data structure, classify the ranges, and find the dominant ingress links. So let's demonstrate the algorithm by a simple example. A short reminder. What we are doing here is performing a traffic-based partitioning of the IP address space. We start with zero knowledge and we follow a top-down strategy for efficiency up to a predefined CIDR mask. Our data structure is represented as a rectangle. In our implementation, we use a binary trie, one for IPv4 and another one for IPv6. To ensure that we have sufficient traffic received, we apply a minimum sample counter as a function of the CIDR mask. So let's start. Traffic entered the network as illustrated by the arrows and is put or collected to our data structure. The color represents the ingress link and the position indicates the source IP. Yeah, now we're done. Now we check if there is sufficient traffic received, what is the case here, and if there is a prevalent ingress link, what is not the case, since we see a wild mix of colors here. So following a divide and conquer strategy, we split the address space. Now we have, we do the, I need here the screen. Now we do the same thing. New traffic is entering the network. So now we have 2 ranges and we do the same thing. We we are looking for if there are enough samples received and if there is a prevalent link. So for the left range, we see sufficient traffic is received, but due to we have still a wild mix of colors, so we cannot make a classification, so we need to split. And for the right one, the minimum sample counter isn't reached yet, so we do nothing. Now, same as before, traffic is entering the network, and now we have another situation. Now we can set a prevalent ingress, since all the traffic of the left/2 range is entering over the same ingress point. For the right range, we cannot make any classification, so same as before, another split is needed. So now we only have one sample for simplicity, and if for a certain, when no new traffic enters for a certain period of time, samples can also expire, which is the case here for the blue one. And now for the reddish ingress point, we see all traffic is coming from the red one, so we also can classify it to a prevalent link. For the left/3 range, we cannot do anything because we also we already reached our CIDR mask for our example, and so nothing is done here. So our implementation, as you can see, our implementation consists of multiple parameters. All in all, there are 6 ones. So it's the CIDR mask or the error margin, or for example, the time bucket length. To find the optimal parameter set, we performed a parameter study with over 300 parameter combinations. Details you can find in our paper. With the final parameterization, we run the IPD in production for over 6 years at a major tier 1 ISP on one single commodity server. And this server is enough to handle the net flow traffic from more than 3,000 border routers with around 4 million flows per second in average. With that, I would give you a sneak peek into our evaluation. We validated the IPD detection accuracy by comparing the detected ingress points with the actual data obtained from 25 hours of net flow traffic traces from the ISP. As you can see on the y-axis, on the left y-axis, the accuracy ratio. The gray shading represents the maximum normalized traffic volume, which represents a daily pattern as expected in the internet. So what we can observe here is that the ingress point detection is able to find the correct ingress link in average in 91% of the cases. But remember, IPD's focus is on high traffic prefixes. So we therefore identified the top 5 and top 20 inbound traffic ISs, which account for 52% and 80% of the traffic respectively. Here, ingress point detection is able to detect almost 98% of the correct prefixes for top 5 ISs. However, there is a small number of inaccuracy that we detail in our paper. In a nutshell, there are sudden traffic shifts or operational changes. So in practice, IPD works well enough for the ISP to build further services on it. Another interesting perspective on ingress point detection is that it enables us to perform the first measurement study on path asymmetry at a tier 1 ISP. Here we compared the ingress routers obtained from IPD with the egress routers we got from BGP for each prefix. At the slide, we see the symmetry ratio on the y-axis over the time. And what we are observing is, yes, there is path asymmetry in the internet. And it depends on the network we are looking at to what extent. Here we observe that the symmetry ratio for tier 1 ISPs are the highest one. And if we are looking at the top 20 or the all the traffic without any filter, we can observe asymmetry ratio ranging from 30 to 40%. So for us, well, so BGP is not usable to implement ingress point detection. An important design requirement, as already mentioned, is that the algorithm must adapt efficiently to the observed ingress traffic dynamics. To evaluate this, we compared the distributions of CIDR mask sizes observed in BGP, shown in gray, with those from IPD, which are the other colored bars. And the comparison reveals notable differences. In 54% of the prefixes in BGP, they are /24, whereas only 15% are /24 in IPD. More notably, in 57% of the prefixes are more specific than /24, and this is relevant because such prefixes are usually not announced in BGP, but are essential for CDN traffic engineering. In this aspect, IPD performs well and fulfills its design requirements. From the operator's point of view, IPD is a valuable tool that improves the ability to troubleshoot their own network. It enables the ISP further to implement additional services such CDN ISP collaborations. But more importantly, IPD is a tool that enables the ISP to talk to interconnected networks in case of any problems. But however, of course, we omitted some points, and one of it is router-level load balancing. Since this requires us to track the source destination IP addresses, which results in a quadratic additional complexity. And since we only observe a small amount of router-level load balancing, we decided to omit that. If you want to experiment with IPD, feel free. We have an open source implementation that we made available in the mini-internet environment with a prototypic ISP scenario, which you can download and run on your own server. With that, I'm at the end of my talk, and thank you for your attention.
Questions? Okay, I'll give you time to think. So, let me warm up with a question. So, one of the things that, one of the assumptions of IPD is that, or conclusions, is that it needs to run very frequently, like at minute level, right? Yeah. Because the dynamics of traffic, whatever. So, would it be fair to say that there are kind of different situations or scenarios, like, for example, you run to allow the operator to have some insight, or maybe it's probably in a longer time scale, as opposed or differently from running at 1 minute level or like 5 minute level perhaps, and to detect an anomaly or something, or even the possibility of having this incorporated or as a building block of a larger system.
Yeah, we could make such enlargement of the time bucket length, but it is not necessary because the resource consumption is not that hard that we need to make such lesser time bucket length. So.
So I was trying to make sure that the 1 minute requirement is not like an artificial challenge.
In production, we do it every minute, but output the results in a 5 minute bin. So we need the 5 minute bins in a productive operating.
Right, thank you. Yeah. Marwan?
Marwan from Cloudflare. I think it's amazing how hard of a problem this is in practice. One question I have is, when you talk about the changes hour by hour, or in particular when you get the split, you said 80% goes one way. Yeah. Did you look to see if the traffic type made the difference? So port number, destination port number, any of these sorts of things, are they would decide, or is it just there's no way to tell, or have you even looked?
We only tracked the source IPs. We had no interest up to now to look at the source as a protocol type, for example.
Okay.
Because we want to the prefixes that have the high volume. So what for content is transmitted, it wasn't an operational problem here.
The only reason I ask is because one could argue is that different types of traffic or different protocols are indicative of different requirements of them, right? So it might be interesting to look at. Thanks.
Thank you.
Still have time for questions? Anyone? Right. Can you go back to? It is there. So I would like to understand this scenario actually. Who is AS1 and AS3? I know you cannot tell me. I mean, everyone knows who is Tier 1 ISP, but what is the situation? I mean, this like multiple Tier 1s peering, and then like the load balancing between this multiple Tier 1.
The situation, you mean where traffic overflows over another AS? Yeah, there is also a paper that in that case it was Apple that shifts the traffic for its iOS updates to other ASs. So very interesting question, yeah, and it was a tool that enabled such a detection for that.
But surely AS1 is not a Tier 2, right? It's not...
Yeah, it's only illustrations.
No other questions? So let's thank the speaker again, please.
Thank you.